Today I will be graphing and analyzing the function f of x equals negative 3x all over x plus 2 to the power of 2/3. To begin, we look at our domain. We must consider what values we can and cannot plug into our function. Because our function is a fraction, we cannot let the denominator of this fraction equal 0. This would occur when x equals negative 2. Therefore, our function is continuous everywhere besides x equals negative 2. In other words, our function is continuous from negative infinity to negative 2 and negative 2 to positive infinity. At this value, x equals negative 2, there is a discontinuity. This type of discontinuity is a non-removable discontinuity because it is a vertical asymptote. As you approach x equals negative 2, the graph will shoot upward or downward to positive or negative infinity. Next, we will consider our end behavior. To do this, we will look at the limit as x approaches positive infinity of f of x and the limit as x approaches negative infinity of f of x. When we plug in positive infinity to our original function, it would yield a very large negative number in the numerator and a very large positive number in the denominator. Therefore, a negative divided by a positive yields a negative infinity. Next, when we plug in a negative infinity to our function, it would instead give us a large positive number on the numerator and a large positive number in the denominator. So this time, the limit would be positive infinity. Next, we will determine our intercepts. It is easiest to start with our y-intercept because all you have to do is plug in 0 for your original function. When we do this, we find that it yields 0, meaning that we get the ordered pair 0, 0. We find that this is also true for the x-intercept because there is no other value to plug in for x that will give us a y-coordinate of 0 besides 0. This means that both our y-intercept and x-intercept will be 0, 0, meaning they will both pass through the origin. The next test we will do is symmetry. To do this, we test f of negative x into our original function. This would yield negative 3 times negative x all over negative x plus 2 to the power of 2/3. When we simplify this, we would get 3x all over negative x plus 2 to the power of 2/3. We find that this is neither an even or odd function, so that means it neither has y-axis symmetry or origin symmetry. Next, we'll test for increasing and decreasing intervals. To do this, we need to find the first derivative of our function. We can use the quotient rule, and by using this, we find that our first derivative is negative x minus 6 all over x plus 2 to the power of 5/3. Using this first derivative, we can find our critical points. This is when the first derivative is either equal to 0 or undefined. We know that our function will be undefined when the denominator is equal to 0, which would be at x equals negative 2. To find when the first derivative is equal to 0, we can set the numerator equal to 0. And by doing this, we can find that it would be at x equals negative 6. We will use these two critical points to create a sign graph for our first derivative. I will note that x equals negative 2 is a vertical asymptote. Now we will test a value into each of these intervals into our f prime function. When we test values to the left of negative 6, we find that they are negative. When we test values in between negative 6 and negative 2, we find that they are positive. When we test values to the right of negative 2, they are negative. This means that our function f is increasing from negative 6 to negative 2 because f prime is greater than 0. This also means that our function is decreasing from negative infinity to negative 6 and negative 2 to positive infinity because our f prime function is less than 0. We can also tell that these critical points are absolute minimums and absolute maximums. X equals negative 6 is an absolute minimum because the f prime function changes from negative to positive. X equals negative 2 is also technically an absolute maximum because f prime changes from positive to negative values. However, because x equals negative 2 is a vertical asymptote, this is technically just a vertical cusp. We now need to consider the y-coordinates of these critical points. We know that x equals negative 2 does not exist because it's a vertical asymptote, so we just need to find what x equals negative 6 is. To do this, we need to plug this into our original function, f. When we do this, we find that it equals 7.1433. We will use this point later on to graph. Next, we will talk about concavity, which deals with the second derivative. Again, we will use the quotient rule to determine what f double prime of x is. When we do this, we find that it is 2 times x plus 12 all over 3 times x plus 2 to the power of 8/3. We use the second derivative function to determine what possible inflection points will occur. These inflection points occur when f double prime of x is equal to 0 or when f double prime of x is undefined. Again, our function will be undefined when the denominator is equal to 0, which is at x equals negative 2. This time, our numerator will be equal to 0 when x equals negative 12. Again, we can use these two inflection points to create a sign graph of f double prime. Again, I will note that x equals negative 2 is a vertical asymptote. Again, we will test values into the second derivative intervals. When we test values to the left of negative 12, we get negative values. Between negative 12 and negative 2, we get positive values. And to the right of negative 2, we also get positive values. This means that our function f is concave down from negative infinity to negative 12 because f double prime is less than 0. We know that our function is concave up from negative 12 to negative 2 and negative 2 to positive infinity because our second derivative is greater than 0. Now we must find the y values of these inflection points. We know that x equals negative 2 is a vertical asymptote, so we just need to find what f of negative 12 is. When we plug this into our original function, we see that it yields 7.756. Now that we have all of our information, we can graph our function. First, we can put down the points that we know. Then by using concavity and increasing and decreasing intervals, we know that our function will look something like this. Here's the graph of f of x.